What's the deal with drinking birds? I mean, seriously, I'm sure just about everyone has seen one before, whether it be a gimmicky item in a toy store, or as something referenced in popular media. But I don't think many people actually know a whole lot about them. Often when people talk about drinking birds, you hear the phrase perpetual motion thrown around a lot, and it's easy to see why. Usually when used in popular media, the idea that they'll dip back and forth forever is used as some kind of visual gag.
Shouldn't you be working?
I got someone to cover for me.
But is that even scientifically accurate? Even looking at the very box that it came in. One of the key selling points is that it'll teach you about perpetual motion. But is that even scientifically accurate? Hi, my name's Elliot, and welcome to my video project for thermal and statistical physics, the drinking bird. In this video, I aim to provide an informative and engaging look into the drinking bird and how it works, so that by the time it's over, you will consider yourself a master of all things drinking bird. First off, no, the drinking bird is not a perpetual motion machine. If it were, I assume we would be living in some kind of futuristic utopian society where all electricity was generated by giant drinking birds. Now, if we want to learn the science behind the drinking bird, the best place to start is with observations. The drinking bird is essentially two glass bulbs connected by a tube, which is attached to a stand such that it can freely pivot. The top bulb has a small beak and is covered in a porous material such as felt. Inside the bird is a highly volatile substance, generally methylene chloride. This can exist as both a liquid and a gas at standard temperature and pressure, along with some dye so you can actually see it. There are three key regions to keep note of: the gaseous region of the head and neck, the liquid at the base, and the gas at the base. Because the tube goes below the surface level of the liquid, the gas in the base and neck are not able to directly interact or mix. When you look at the bird in action, the first thing you notice is that it doesn't ever start moving until you manually dip its head in the water. After this, the liquid in the base of the bird begins to rise up the tube. Eventually the bird pivots and dips its beak back into the water. This cycle repeats itself, seemingly forever. I can certainly see how people get the idea that this comes from some form of perpetual motion, but there's actually a surprising amount of physics at play here. There are three key physics principles that lead to the motion of the bird, but individually, none of them are much more complex than something a high schooler would know. So first we must ask the question, why does the bird dip its head at all? The answer, our first principle, is quite simple. It's unbalanced. As you may have noticed, the bird does not sit straight up in its resting position. Rather, it's at a slight angle, so that the head is on the opposite side of the pivot point to the body. When the liquid is raised high enough, the center of gravity shifts beyond the pivot point, causing the bird's head to go down. It's basically just a seesaw. Second question, why is the water necessary? When the bird's beak is initially dipped in the water, the felt covering it will absorb some, hence the drinking in the name. To explain why the bird needs to drink water, first I need to explain the second key principle. For a substance to change from a liquid to a gas, it requires energy. This is known as the latent heat of vaporization. In this instance, the energy comes from the bird's head, which lowers its temperature. This is an example of evaporative cooling. The same principle is used by the human body to cool us down when we sweat. I'm aware that in answering the second question I've raised an even larger one. Why does the bird's head getting cooler drive the motion? Well, to answer that, first I need to explain the third key principle, the relationship between temperature and gas pressure. Temperature is directly related to the average speed of all the particles in something, and pressure is the force a gas exerts due to particle collisions. As the speed of the particles in a gas increase, the number of collisions per second will increase, and therefore the pressure will also increase. From this you can see that pressure is directly proportional to temperature. This is also shown through the ideal gas law. As previously mentioned, the gas in the head and the base of the bird cannot directly interact. Rather, they're both exerting a pressure on the liquid separating them. When they're at the same temperature, this pressure is equal. However, as the head cools, its gas pressure drops. Also, due to the volatile nature of the substance, the gas will start to condense back into a liquid, further dropping the pressure. Now the pressure on the liquid is imbalanced, and the higher pressure gas in the base will push the liquid up the neck. As previously mentioned, this leads to the bird tipping over. Crucially, when the bird does tip, there's a small period where the gases in the head and body can freely mix and return to thermal equilibrium. Because of that, this process can repeat for as long as there is water to be evaporated, and that is the full cycle of the drinking bird. Obviously, this can't be left as pure theory. Some investigative fieldwork would need to be done. I decided to measure the temperature change of the gas in the bird's head over time. Unfortunately, this is much easier said than done, as the bird is sealed, so the only way to measure the temperature is by attaching a sensor to the outside and allowing it to cool through conduction, which is a slow process leading to imprecision. Another issue is that due to the process being reliant on evaporation, it's much faster when there's less moisture in the air. However, when I was able to perform tests, the humidity was upwards of 70%, which led to a lot of waiting around. Ultimately, I decided to blue tack a thermistor to the back of the head. However, because of the extra weight this added, the bird would no longer dip. As such, I had to manually dunk the bird once the liquid reached the top, to simulate its natural movement. This further removes the experimental data from ideal conditions. Quite unsurprisingly, due to the imperfections in my methodology and the imprecision of my sensor, the data itself is not the most exciting. The sensor would not pick up any small change of temperature in an individual cycle, however over time, the internal temperature of the whole bird did appear to decrease, likely due to the evaporation of water. Although the data on its own doesn't tell us much, a lot can be learned by comparing it with data from a slightly altered experiment. I don't know about you, but when I first learned the reason the bird moved was because the head was cooled by water, my first question was, what happens if you use boiling water? Surprisingly, it's not that different. Looking at the data, you can see there's a spike in temperature whenever the bird drinks some boiling water, but it pretty quickly evaporates and cools the head, leading to the normal cycle. One thing to note is that over time, the temperature of the bird as a whole did appear to increase due to the equilibrium temperature being higher than it initially started. I also decided to do a few more simple tests to further verify the theory. What I realized was that the reason liquid is forced up the tube is because of a pressure difference. I wanted to see if instead of cooling the head you could heat the body for the same effect, as this would increase its pressure. There are quite a few different ways to test this, such as simply holding the base of the bird in my hand, where my own body heat was enough to raise the gas pressure. I also used a hairdryer to quite pleasing results, and obviously you can't do science without playing with a little bit of fire, so of course I tried heating the body using a candle, which had a similar effect. Another thing to consider was using a substance other than water to cool the bird. I decided to try using an alcohol-based hand sanitizer that was 65% ethanol, as ethanol has a substantially lower heat of vaporization than water. What this means is that in theory it will evaporate much quicker, cooling the bird down faster, and the results support this. Although the experiment was done on a separate day where the humidity was even higher than it was for the water tests, the drop in temperature of the bird's head was much faster. From these tests, it's quite apparent that the theory behind the drinking bird was correct. The change in pressure due to the change in temperature is the source of the bird's movement, and the evaporation of water on the head is what causes the change in temperature. And finally, to answer the question I'm sure you've had burning inside of you since the start of this video, no. The Simpsons, Season 7, Episode 7, King-Sized Homer, does not feature a scientifically accurate representation of the drinking bird.